So I'm waiting for a few minutes for others to join, and then we can start. Okay, so just wait for a few minutes. Hello and welcome everyone to today's live class session on the week 5. This course is being taken by Professor Shagota Dasgupta and Professor Shomode of IIT Kharagpur, myself Srijan Sen, and today I would be discussing the week 5 lecture slides. And the way I usually take is that first I discuss in brief the lecture slides in brief, and then we go about solving a few question and answers, say, of previous years, and some few interesting questions that will help in solving your assignments, and as well as it will help you in taking up the future exams that come. So these questions are basically not restricted to these questions are basically restricted to your week 5 slides, but these questions will definitely help you also in your competitive exams and all. Okay, so let us begin. So I'm sharing my slides, kindly confirm. So is my slide visible to you all? Means my screen. Is it visible to you all? Okay, good. So in today's class, we would be discussing mostly about chromatographic techniques. So in today's class, we will be mostly discussing about the chromatographic techniques. So in the previous lectures, what we talked about is mostly your buffers. Then we spoke about the building blocks of proteins, that is amino acids. We spoke in the third lecture, we discussed about the spectroscopic techniques, the different measurements that we take up by finding the concentration of the proteins and all. And in the last class, we discussed about proteins, the protein folding and the protein denaturation. Now we need to understand how can we, so we have proteins in hand. Okay, or we know what proteins are, we understood what protein folding was, protein unfolding was, but how do we separate proteins? That is very important to understand. Purification of proteins from a crude extract or purification of proteins from other proteins, separating proteins. This concept comes under the category of chromatographic techniques. So briefly talking about the protein structure, as we all know that all proteins are composed of amino acids which are linked together by peptide bonds. And there are 20 naturally occurring amino acids which forms the building blocks of proteins, each with a characteristic side group that determines the properties of amino acids, like whether the amino acid is acidic or it is basic or neutral, whether it takes part in providing absorbance to the protein, giving absorbance of the particular protein, or is it forming the hydrophobic core or interacting with the water molecules by forming hydrogen bonds. So all of these informations can be understood by seeing the structure of that particular amino acid and determined from the side chains. So proteins are composed of one or more peptide chain in a three-dimensional structure, which includes linkages with non-protein molecules such as lipids and carbohydrates. So protein forms different structures. We saw that it can form different structures like the primary structure, secondary structure, then it has a tertiary structure, and then finally the quaternary structure. And then comes the concept of protein macromolecule interaction that also includes non-protein molecules, like you have the lipids, carbohydrates, sometimes also proteins, and even small molecules or ligands. And the combination of number and type of amino acids and the non-protein component of the tertiary structure determines the properties of the proteins. So let us introduce you to chromatography. So a goal of biochemistry is to separate and identify chemical compounds. So chromatography is one of the most effective techniques for accomplishing this separation and identification from different or a mixture of chemical compounds. What happens in chromatography? It's that the substances are placed in a system consisting of two physically distinguishable components. Mainly the two components includes your mobile phase and the stationary phase, and molecular species separate because they differ in the distribution based on the two phases. So on the basis of how we are going to separate them, we categorize these types of chromatography, and the categories include absorption chromatography, partition chromatography, ion exchange chromatography, molecular sieve chromatography, affinity chromatography, and then we have the column, paper, thin layer and gas chromatography. So these are the many of the lots of types of chromatographic techniques that we have in hand, and these are the techniques that are basically used to separate and identify your proteins, your desired proteins from a mixture or a crude extract. Okay, so you can separate them, identify them, purify them. That is what we want to get, the pure protein or the pure compound that will help us in carrying out the experiments in a much better manner. So what is the main aim of purification? So the typical reasons for purifying a protein may be to identify the function of a protein, like we have the enzymes. If it is present in a mixture of proteins, it does not usually carry out its catalytic function or its enzymatic action. So to identify the function of that particular enzyme or that particular protein, we need to purify it. Also, we need to identify the structure of the protein, like we carry out NMR, X-ray, and nowadays cryo-EM is very relevant. So this is the another reason of getting the protein in a pure form. Otherwise, we get random data that is just not very helpful in finding out the structure of proteins. And the other reasons includes to use the enzyme to generate a desired product as a part of the research project to produce commercial products such as a therapeutic or diagnostics. Like sometimes there are you say drugs and all that needs to be in the purified form to act as therapeutics. Okay, so these are the few of the reasons for purifying a protein. So what are the key steps in purification? While no two purifications are the same, and the separation scientist is faced with a bewildering variety of techniques available to achieve their goal, the majority of the purifications aim to achieve the same result. So these are, what are these uh, basic aims? So release the target protein from the starting material, like I was mentioning the crude extract. So you have to get your desired protein from the starting material. Removal of solids to leave the protein in the supernatant. Removal of water to concentrate the protein. Removal of contaminants to achieve the desired purity, and importantly the stabilization of the target protein. So these are the very important steps for in purification, beginning with separating it from the crude extract, then performing the purification in such a manner that your protein is present in the soluble fraction, that is the supernatant. In the soluble fraction, if you get in the pellet, it becomes very difficult, or in the insoluble fractions, in the say in the pellet or the insoluble fraction, it becomes very difficult to actually extract your protein from that clump form. And then you have to concentrate the protein to get a desired concentration to carry out experiments. Then you have to remove the contaminants, some ions and all, and then you have to stabilize the target protein to carry out different functional experiments. So the first type of chromatography that I would be discussing here is size exclusion chromatography. So we all know what is size exclusion chromatography. It is also known as the gel filtration or the gel permeation chromatography, and that uses porous particles to separate molecules of different sizes. And this size exclusion chromatography is generally used. Just a minute. Okay. So the size exclusion chromatography is generally used to separate biological molecules and to determine the molecular weight and the molecular weight distribution of polymers. So these are the very important points. It is used to separate biological molecules, determine the molecular weights and molecular weight distribution of polymers. It is usually applied to large molecules or macromolecular complexes like we have the proteins and industrial polymers. So when an aqueous solution is used to transport the sample through the column, the technique is known as gel filtration chromatography. When an organic solvent is used as a mobile phase, the technique is known as gel permeation chromatography. And the separation of molecules is called fractionation, and the size of the pores in beads determines the exclusion limit. What is the exclusion limit? What goes through the beads and what goes around the beads. Okay, so what goes around the beads takes a longer time, or sorry, takes a shorter time, and sometimes it goes into the void volume. But what goes through the beads takes time in eluting, and there are different sizes of beads, so in that manner we can separate out the molecules or the compounds based on their size. So what is the principle of size exclusion chromatography? Let us see. So a mixture of molecules is dissolved in a liquid, the mobile phase, and is applied through the chromatographic column, which contains a solid support in the form of your beads or microscopic spheres, and that is what we call as the stationary phase. The protein in the buffer or the compound in the buffer is the mobile phase. The mass of beads within the column is often referred to as the column bed. And what do these beads usually do? These beads act as traps or sieves and function to filter small molecules which become temporarily trapped within the pores. What happens then? The larger molecules pass around the beads and they are excluded from the beads, and therefore they take less time in eluting. So the larger molecules cannot penetrate, or they partially penetrate the pores, whereas the smaller molecules can access all the pores. Thus what happens is that the larger molecules, what they are doing, they are not entering the pores, rather they are going out. They are not entering the beads, they are going out of the beads to elute first. So the larger molecules are eluting first, the smaller molecules elute later, and while the molecules that can access all the pores elutes at the last. So what does that mean? So let us imagine that there are numerous sizes of pores. So the larger molecules can enter only the larger beads, or they do not enter at all. So they elute faster because the path length is very less for them. Whereas for the smaller molecules or the medium sized molecules, what happens that they can enter most of the pores rather than just bypassing that. Hence they have a longer path length, and based on the size, the smaller the molecule, the higher the time they take to elute. So higher will, so at the end you would be seeing the smaller molecules to be eluting. So particles of different sizes will elute through the stationary phase at different rates. What is important is that the larger molecules elute first, smaller molecules elutes later. So this is the principle, and you can see the mobile phase over here that is being poured, and this is the beads that you can see, and your particles starts going through these beads. So the smaller molecules, you see the smaller molecules have to enter all of these pores and cross all of the lengths and go. But what happens to the larger molecules? They can simply bypass. You can see this molecule, this can simply bypass the pores and do not enter the pores, and hence they reach the bottom of the column at the beginning and they elute faster. Okay, so the mixture is added to the column containing the cross-linked polymer. The proteins separate by size. Larger molecules pass more freely, appearing in the earlier fractions. So very small molecules enter many pores of the gel, equilibrating between the gel and moving buffer, and so they travel slowly. Medium-sized molecules enter some pores in the gel, equilibrating between the gel and the moving buffer, and the larger molecules enter few pores in the gel, so they travel rapidly and are eluted sooner. Okay. So if you look at the mathematical principle, so the total column volume or VT is equal to your volume occupied by the packing plus volume of the solvent in the pores plus the free solvent volume, that is similar to the injection volume, and the addition of all of this gives you the total column volume. So what are the different components of the size exclusion chromatography? We have the stationary phase, that is the beads, the pockets, the mobile phase. Am I audible? Am I audible now? Yeah, good. Okay. So the different components of the size exclusion chromatography includes your stationary phase, that is you can call the beads or the pockets. We have the mobile phase where you have the protein in a particular buffer, the columns, the pumps that is involved in the movement of that protein. Okay, and finally is your detectors that will be measuring the your graph. That is, you get a graph like this. Okay, you get a graph, you get peaks like this, so it is determined by the detector. So in general, what is a stationary phase? So the stationary phase is a semi-permeable porous bead which is well defined range of pore sizes. The beads are basically your cross-linked polymers. Then the degree of cross-linking is basically controlled to yield different pore sizes. The smaller pore sizes are used for rapid desalting of proteins and for protein purification. Then the intermediate pore sizes are used to separate relatively smaller proteins, and very large pore sizes are used for the purification of biological complexes. So stationary phase used for gel extraction exclusion chromatography includes your dextran or the Cefadex TM polyacrylamide and dextran polyacrylamide cephacryl TM. So these are the different components that are used in the stationary phase when you perform SEC. So if you have seen SEC column, so the packing is with this either dextran or polyacrylamide, like you have the cephacryl TM, and each is available with a variety of different range of pore sizes in the beads that permit separation of the macromolecules of different sizes. Like some say is that up to 200 kilodaltons. Some have a capacity to separate up to 600 kilodaltons. Some have 100 kilodaltons. So any size above that particular limit will elute in the void volume. That is, it cannot enter any of the pores and it just elutes in the void volume. So you get a peak in the beginning. That means your protein has eluted even before the run has actually started. So it cannot separate above that particular limit. So what are the properties of a good stationary phase? That is that it should be chemically inert. It should be definitely be inexpensive. It should not react with the your protein or the compound that is to be separated. It should not react with your elutant, and also it should be colorless, uniform in size and shape. Along with it should be properly stable. It should not be broken or crumbled or cramped like that. Now we have the mobile phase. So in usually the mobile phase is your protein or the compound that you want to separate, or the mixture that you want to basically separate. So the liquid used to dissolve the biomolecules to make the mobile phase is the buffer. The mixture of biomolecules that we dissolved in the buffer is the sample. So we prepare samples that can be protein sample, small molecule compound samples and all. Then the choice of the mobile phase to be used in any separation will depend on the type of separation to be achieved and the component to be separated, and the different the commonly used diluents for the polymers that dissolve at room temperature includes tetrahydrofuran, chloroform, dimethyl formamide. So for synthetic elastomers, polybutadiene, polyisoprene, the solvent is toluene. For your PVCs, styrene, butadiene, then rubber, epoxy resins, we have the tetrahydrofuran. Then for polyurethane, we have dimethyl formamide. For polyolefins, we have trichlorobenzene. For proteins, polysaccharides, we have waters, buffers. Usually we use buffers. So this is the, if you can see you have the column, then you have the loop where you inject. So this is the injection valve where you inject your protein, and this is your mobile phase where you have the buffer. So here in the injection valve you inject your protein and it goes inside this particular loop, it stays inside this loop. Now when you start the pump, the mobile phase is sucked and it goes above the loop. So it starts and it goes above the loop, it goes, and when it starts eluting it, so this is the column, the SCC column, then you have the detector, and then you have the data station where you collect all the data. So in all this the game of separation happens in this particular column and is detected in the detector. So basically we need to keep in mind that the protein is injected through a particular valve and it stays inside this um, loop region. Okay, and then when we pass the buffer through it, it just pushes it through this column and helps it to elute at different rates. If it's a larger molecule, it elutes faster. If it's a smaller sized molecule, then it elutes at the end of the uh, curve. So another important thing is component of this uh, size exclusion chromatography is pumps. So a highly constant rate flow is very important to be maintained during the entire chromatography. Like a particular, the constant flow rate is very important. There cannot be randomly, you cannot have a gradient of flow rates, or you cannot keep the flow rate fluctuating. So that is very important thing in SEC. For that we use pumps. A change in the flow rate by only 0.1% can cause an error in molar mass up to 10%. So you can imagine how big the error bar becomes for only a change in flow rate of 0.1%, and most pumps can only reproduce the flow rate of 0.2 to 0.3%, and inline filters in the solvent reservoir can prevent particles from coming into the pump heads, which might damage the check valves or the pump shields. And the different types of pumps includes your syringe pumps and the reciprocating pumps. Is it visible now?
Yes, now it's visible.
Okay. So another important component is detector. So the concentration, so we have the concentration sensitive detectors and the molar mass sensitive detectors. So the concentration sensitive detectors have your bulk property detectors to measure the refractive index. Then you have the solute property detectors for the ultraviolet absorption. You have the evaporative detectors for the evaporative light scattering measurements. Then for molar mass sensitive detectors, you have the light scattering detectors, the low angle light scattering detectors, and the multi-angle light scattering detectors. So the applications of size exclusion chromatography includes your protein fractionation, purification, then understanding or determining the molecular weight, separation of a mixture of compounds like sugars, proteins, peptides on the basis of their size. It also helps to determine the particular compound even in the polymeric structure or the for proteins, we even if we have a quaternary structure or an oligomer formation, it can determine that. So ACC is basically used for purification and analysis of biological polymers such as proteins, polysaccharides, nucleic acid, and various species of RNA and viruses have been purified using agarose gels. So this can be purified using SEC. And then for desalting experiments and copolymerization studies, ACC is a very nice technique. Coming to the next type of chromatography is the affinity chromatography. So this technique offers high selectivity, high resolution, and usually have the high capacity for the proteins of interest. So purification that would otherwise be time consuming, difficult, or even impossible using other techniques can be often achieved with affinity chromatography. And the technique can be used to separate active biomolecules from denatured or functionally different forms to isolate pure compounds present at low concentration in larger volumes of crude sample, and also to remove specific contaminants. So if you see that the principle behind this affinity chromatography is that you inject your mixture, you have something that binds well with this particular compound. Okay, so you have a, say, a tag or a particular ligand that binds to your object material. So it goes and binds, it catches your target protein, and then comes the absorption of the object materials. Then you wash out the impurities, the other unbound substances, and then you use a particular buffer or a particular compound that binds more tightly to this particular ligand, and your object materials opens up or your target protein opens up and then elute. So what is happening? There comes the concept of tighter binding, or your say one the compound that binds more tightly is relevant over here. So first is you have a particular ligand that binds to your object material, and there you do not have any competition for the binding. Okay, then in the end when you are eluting your material, there comes the concept of competitiveness, and there your ligand binds to your that was already bound to your particular protein, or the object material is opening up and it is binding to something that is has a better affinity or a more higher affinity towards this particular ligand. Okay, so this is one of the apparatus of affinity chromatography. So affinity chromatography separates proteins on the basis of a reversible interaction between a protein and a specific ligand coupled to a chromatographic matrix. So the kinds of elution that we usually observe is the pH elution, ionic strength elution, reduced polarity of eluent, competitive elution, and the chemotropic eluents. So you see it binds over here. So this is already fixed. to the matrix, and then your proteins come and binds over here, and then when something else binds here more tightly, this opens up and that just keeps binding. So what happens, the simplest case is that a change of buffer composition elutes the bound substance without harming either it or the ligand. Then when you change the pH, or higher concentration of chemotropic agents are required for elution, that may cause a temporary or a permanent damage. And methods 3 and 4 includes a specific elution by adding of a substance that competes for binding. These methods can enhance the specificity of media that use group specific ligands. So it comes and so it's bound. So you have a material that binds to your protein, so it helps it in eluting. If it binds to the matrix ligand, so that also helps in eluting your protein. The other is just changing the pH, and the first one is changing the buffer composition. So buffer composition change, pH change, and the competitive binding. So what are the steps of purification? So first is the equilibration step, where you use 1 to 2 column volumes for washing off or for equilibrating your column with that particular buffer. Then comes the loading or the absorption of the sample to the eluent of the unbound material. So there you are loading your particular sample, and it is binding, and when it reaches a stationary phase, and then you change the buffer composition. So then you wash away the unbound material, and that is also about 1 to 2 column volumes, and then you elute your bound protein by changing the buffer composition, and you see a sharp peak. And after this, the re-equilibration for the next person to use. So first is equilibration with the lysis buffer or a buffer A. You do that, then you have the absorption of the sample and elution of the unbound material. Then you wash away the unbound materials, and then you finally elute it by changing the, say, pH, or by changing the buffer composition. And finally is the re-equilibration for the next person who is going to use it or perform the purification using that particular column. So these are the this is the column that we basically use for carrying out affinity chromatography. And if you can see from here, you see that so this is the binding buffer. So it is binding, and then you change the buffer composition, and your protein starts eluting. So okay, and then you have the flow through of the unbound material, and this is your eluted target, where you do not change the buffer composition. Or it sometimes happens that your the protein concentration might be low, or the protein might not give very good absorbance. So because of many reasons, you do not get a proper band. But that does not mean you do not have proteins. It can be of various reasons. But the ideal situation is this. But from these two figures, what you can understand is that you need to change the buffer composition to get a particular peak. If you do not change the buffer composition, you only get a very low absorbance wala peak, and that is not that indicates that your protein has not eluted. But sometimes it occurs that even if you change the buffer composition, your protein might not elute. There can be several reasons for it. One is that the composition of the buffer that you are using might not be correct. The second is that your protein does not absorb well. So because of that, you get very low absorbance, because the molar extinction coefficient of your protein might be very low due to lack of tryptophan or tyrosine residues. And other thing that it might have not bound to that column, so you might get your protein even in the flow through. So different reasons, different ways of troubleshooting all of these. But the ideal situation is the sharp peak that you get for your particular purified protein. Okay, so there can be different conditions or situations that might arise. For, like I was mentioning, even when you change the buffer composition, your protein might not be eluted. Okay, so these are few, or the peak might be very small. Okay, and sometimes what happens, no, this is a very nice situation, okay, because you are actually loading your protein in small amounts. So your protein might be loaded in small amounts and then you get a sharp peak. So this is the ideal situation what you should be observing. And sometimes you observe is that you get 2 to 3 peaks, or one peak might be a shoulder of the other peak. So that is a very complicated situation, and purifying all of those fractions becomes very difficult. But for that, in that case, what you can do is that you can purify the protein using size exclusion chromatography. There comes no concept of affinity, and there you can separate the proteins if they are forming oligomers or they are of different sizes. Now let us talk about matrix. What's a matrix? So the proper selection of matrix or a carrier for the ligands. So matrix is a carrier for the ligands that is important for the successful applications of stereospecific adsorption. Like for insolubility, then for sufficient permeability, it should have zero adsorption capacity. Then it should be highly rigid and should be have suitable particle form. The chemical stability under the conditions for adsorption, desorption, and regeneration should be they should be chemically stable. Then the chemical reactivity should be high enough for allowing ligands and spessures to be introduced. It should be resistant to enzymatic or microbial attacks. It should have a good flow property for rapid, fast separation. And an open pore structure ensures high capacity binding even for the large biomolecules, such that different size of molecules can also be separated. So these are the different characteristics of the matrix that we can use, or the different companies that they use, keeping in mind all of these characteristics. So no matrix support is ideal in all these respects: porous glass, cellulose, polyacrylamide, and agarose. Okay. Now, how do we select the ligand? So we spoke about matrix. Now, how do we select the ligand? There should be a few characteristics features of the ligands as well. So the selection of the ligands for affinity chromatography is influenced by majorly two factors. Is that the ligand must exhibit specific and reversible binding affinity for the target substance. So it should not only be specific but also it should be reversible. It must have chemically modifiable groups that allows it to be attached to the matrix without destroying its binding affinity. And the dissociation constant for the ligand target complex should be ideally in the range of 10 to the power minus 4 to 10 to the power minus 8 molar. That is, it should not be very high or it should not be very low. It is ideal. So now we are left with only the ion exchange chromatography. So up till now, if you have any questions, you can ask me. So mainly I spoke about the size exclusion chromatography, the affinity chromatography, and the different components of these chromatographies. So up till now, if you have any questions, you can ask me. Then we will start with the last type of chromatography, that is the ion exchange chromatography. So no questions? Okay, good enough. So let us start with the ion exchange chromatography. That is the last type of chromatography that we would be discussing. So ion exchange chromatography, from the name as you can understand, so separation based on charge. So ion exchange chromatography may be defined as the reversible exchange of ions in the solution, with ions electrostatically bound to some sort of insoluble matrix or stationary phase. So this technique is extremely useful in the separation of charged compounds like proteins differing by only one charged amino acid. So it is critical in that aspect. And then this technique, so in ion exchange chromatography technique, one can choose whether to bind the substance of interest and allow the contamination to pass through the column, or vice versa. So it binds, say you have an anion exchange chromatography where you have negatively charged molecules bound to the matrix and your protein is positively charged, so only your protein binds but others do not. So in that manner you can just remove the uh, contaminants from binding. Next up, this technique has been developing since the 19th century. That was firstly used in the purification of water, and this ion exchange chromatography is a distinct principle of chromatography performed in a column. So the principle behind ion exchange chromatography is the attraction between oppositely charged stationary phase, also known as the ion exchanger and analyte. The ion exchanger basically consists of inert support medium coupled covalently to an anion exchanger or cation exchanger functional groups. Now, to these covalently bound functional groups, the oppositely charged ions are bounded, where you have the mobile counterion, which will be exchanged with like charge ions in the sample having charge magnitude more than the ions bounded to the matrix. Thus, if anion exchange chromatography is performed, negatively charged sample components will interact more with the stationary phase and will be exchanged for like charged ions already bound to the matrix. So the working principle is that let us assume or consider a column having E minus Y plus cation exchanger, in which E minus is negative charged exchanger and Y plus is the mobile counterion. So let X plus be the cation in the sample where having charge greater than Y plus. So the X plus ion can exchange sites with the counterion Y plus with satisfying the following relationship. So E minus Y plus, then you have X plus. So just the charge on the Y plus is X plus is more. So E minus is more tightly binding to X plus than the Y plus. Plus then you have the remaining neutral and the negatively charged particles. So the bounded cation X plus can now be eluted by either two ways: by adding a component M plus having the charge more than that of X plus, so that M plus will replace the X plus and X plus will be eluting, or by changing the pH of the solvent such that X plus has no charge and then the unbounded from the matrix can be eluted out. So in two ways you can do the elution: changing the pH or using a molecule that has a higher charge than the your protein of interest. So that can be higher positive charge or higher negative charge. So the factors that affects this ion exchange chromatography is the ion exchange raising, where you have the swelling factor and the cross linking that is important for the effective separation. The cross-linking should be controlled as it affects the exchanger's capacity, and swelling helps in proper exposure of charged functional groups for exchange of ions. So less swelling, separation of ions of different sizes becomes difficult. So higher swelling, the separation is more feasible. Then is the nature of the exchanging ions, where you have the valency of the ions, size of the ions, polarizability, concentration of the solution, and the concentration and charge of the ions. Apart from these two, we have the pH of the mobile phase. The ionic strength mostly interferes with the chromatographic techniques. You have the mobile phase modifiers, temperature, and the buffer. So buffer, so the pH also falls in the category of buffer. So the pH of the buffer should impart some charge to the sample ions as present in the column. Like anionic exchange chromatography should be carried out with cationic buffers and vice versa, because buffer ion will indulge in ion exchange that will be of no use. So it will be just interfering and create more of trouble. So we all know one concept, that when the pH of the buffer is less than that of the pi of the protein, your protein will be positively charged, and when the pH of the buffer is more than the pi of the protein, the protein will be negatively charged. So the classification of ion exchange resins. So according to the chemical nature, they can be classified as strongly acidic cationic exchanger, where you have the sulfonic acid groups attached to styrene and divinyl benzene copolymer. You have the weakly acid cation exchanger, where you have the carboxylic acid groups attached to acrylic and divinyl benzene copolymer. You have the strongly basic anion exchanger, where you have the quaternary ammonium groups attached to styrene and divinyl copolymers. And weak basic anion exchanger, where you have the polyalkyl amine groups attached to styrene and divinyl benzene copolymer. So whatever is the thing, it's mostly either attached to styrene and divinyl benzene copolymer, or the acrylic and divinyl benzene polymer. So if it's a strong acid, you have the sulfonic groups. If it's a weak acid, you have the carboxylic groups. For strong base, you have the quaternary amines, and for weak base, you have the polyalkyl amine groups. So the applications of ion exchange chromatography is softening of hard water. Then you have demineralization of water to analyze base composition of nucleic acids, to concentrate the metal ions in the sample, to measure the additives in food and drug samples, then to separate protein mixtures, extraction of enzymes, purification of solution-free ionic impurities, then separation of sugars, amino acids, proteins, and other separation of different salts like inorganic ions and all. Okay, so these are the different applications of ion exchange chromatography. So these are the three major chromatographic techniques that we usually use in daily life. Apart from that, there are many other chromatographic techniques that also carries out the separation of proteins in a better manner. But these are the commonly used chromatographic techniques, and the different applications of these techniques in the different aspects of biological molecules or the separation techniques. And so that is all about the that was all about the discussion of the different techniques. Okay, now we will be jumping into the solving of questions. That is the most. Hello, hello, hello,
Hello, sound episode.
hello. Can you mute yourself if you have to say?
ଇଏ କଲାନି କଣ କହିଲୁ ମେସେଜ ବନ୍ଦ କଲାନି
Okay, so how I solve the questions is that I give you the questions, you answer me back, and you can answer me in the chat box, so such that the answers remain, and then I would be discussing with you the answers if you have any difficulties and all. Okay, so I guess the lectures were clear to you all. That's not a problem. If you have any question, you can definitely ask me. In the meantime, we can start solving the question and answers. Okay. So let's start with the first question. A particular protein can be separated from the contaminating proteins by mass spectrometry, fractional distillation, chromatographic techniques, and centrifugation. So which option or options do you feel is or are correct? You can answer in the chat box. I want all of you to give me an answer such that I can understand that how clearly you people have understood. Okay, I've got one answer. What about others? So the question says a particular protein can be separated from other contaminating proteins. So the separation technique. Okay, no other answer. Okay, so the correct answer over here is C, chromatographic techniques and centrifugation. Why centrifugation? Because centrifugation helps to separate the proteins based on their molecular mass. Okay, so higher the mass, the it will be at the bottom, it will be settled at the bottom, and then different layers are basically formed. So in the basis of that, the centrifugation techniques. Mass spectrometry does not help in separation. It gives us only the mass or the molecular weight of that particular protein, but you can separate them actually. Anyways, the next question is, if the partition coefficient is doubled, then what factor change, then by what factor will the molecular weight change? Okay, so let us see how to answer this. So K average is doubled, that is equal to 2 K dash, let's keep it average. So what do we know? K average is equal to ln of molecular weight. Now what happens when it is doubled? So it becomes, so K average becomes 2 ln NW. or if we take it inside, it is ln. Okay. So if you think in terms of MW, it is the power square. So this is the correct option. Okay. Okay, the next one. The question says, which of the following statement is or are true in the above graph for gel filtration chromatography? So for gel filtration chromatography, which of the following statement is or are true? A and B are more distinctly separated than that of C. B is dimerized form of A. If buffer rate is increased, the peaks will get more separated than the original. The molecular weight of C is lower compared to A and B. So which answer do you, or which option do you think is correct? Everyone please answer. Okay, I got one answer. Anyone else would like to try? Okay. So let us go one by one. A and B are more distinctly separated than that of C. No, first of all, A and B are not separated at all. So they are not separated. Now B is the dimerized form of A. There is, first of all, dimerized form of A. If it would have been dimerized, it would have been on the higher molecular side, but it is on the lower molecular side. So this is incorrect. If the buffer rate is increased, the peaks will be separated more than the original. That is also incorrect. So the slower the buffer rate, the more resolution would for your separation would that be. And the molecular weight of C is lower compared to A and B. That is the only correct option. So D is correct. Now coming to the next one. Void volume in gel chromatography column. So void in gel chromatography column refers to. So what is the void volume? Is it space within the matrix pore, or is it volume of the column, or is it volume of the column which is unoccupied by the matrix granules, or is it volume of the protein added to the column? So what do we call the void volume? Yes, very good. So C is the correct answer. So it is the volume of the column which is unoccupied by the matrix granules. So what do we get in the void volume? When a particular protein of that has crossed the limit of the separation, or that lies above the separation limit for that particular column, it comes out as the void volume. So therefore it is the volume of the column that is unoccupied by the matrix granules. Very good. Okay. Now the next question. In a size exclusion chromatography, Sephardex G200 is used. The column volume is given as 60 ml and the volume of the stationary phase is 45 ml. If the elution volume of the solute is given as 40 ml, find out the distribution coefficient. If you know the equation, you can try. Otherwise, I would be definitely discussing. So nothing to worry. If you know the formula, you can definitely try. So what is mentioned? The column volume is mentioned, that is 60 ml. The volume of the stationary phase is mentioned, that is 45 ml. And the elution volume is also mentioned, so that is 40 ml. So okay, let us do it then. So let us first write down what is mentioned. So V0, that is your void volume, that is equal to, so first the column volume is mentioned. So your void volume is 1/3 of column volume, that is into 60. So that is 20 ml. Okay. Next up, what we have is volume of stationary phase, Vs, that is 45 ml. And VE, that is your 40 ml. That is given. So now coming to the formula. So KD, that is your distribution coefficient, is VE minus V0 divided by Vs. So keep this formula in mind. Vd equals to VE minus V0 divided by Vs. So what is that coming up to? So 40 minus 20 divided by 45. So it is coming around 20 divided by 25. So about 0.44. So A is the correct option. I guess it is clear. So first you have to find out the void volume. After you get the void volume, you know what is the stationary, the elution volume and the volume of the stationary phase. You subtract the elution volume from the void volume divided by the stationary volume of the stationary phase, and you get the distribution coefficient. If it is clear, let's go to the next question. Which of the following will improve the efficiency of separation in liquid chromatography? So to improve the efficiency of separation in liquid chromatography, what do we need to do? Increase the sample size, increase the column diameter. Reduce the sample size, increase the column diameter, increase the sample size, reduce the column diameter, and reduce the sample size, reduce the column diameter. Usually that is the answer most people would be giving. So reducing the sample size is very correct. but increasing the column diameter will also affect, number one, the path length. That will also be involved in the dissociation factor. Your protein or your sample would be more dissociated. That would never help in the um, in increasing the resolution. Rather, there should be an ideal column diameter. So reducing the column diameter helps in the increasing the or improving the efficiency of separation. Reducing the sample size is very nice, that will we know why, but what will increasing the column diameter do, it is that it is increasing the surface area. So the dissociation of the molecules will be more. So more dissociated your molecules go, the lower will your resolution be. So we need to reduce the sample size as well as reduce the column diameter. Okay. The next one, three different proteins are to be separated for analysis. The characteristics of the proteins are given below. Which of the following would result in best separation of these proteins in order to get them in pure form? So is it paper chromatography, gel filtration chromatography, SDS page followed by ion exchange chromatography, and ion exchange chromatography followed by gel filtration? So here you have the molecular weights of 13.3, 27.5 and 63.4, and the PI is 9, 8.7 and 9.5 respectively. So what would you do in this scenario? Which type of chromatography would you be performing over here? The PIs are more or less similar. What varies is the molecular weight. No. When you're performing an SDS page, what happens is that we do not know whether this protein B or protein C is a dimer or a tetramer of protein A, because you see this into 2 is 6 point around 26.6, and when you multiply it by 4 it is 60, how much is it come, so 2652. Okay. So fine enough, you can do a size exclusion, SDS page, but followed by ion exchange chromatography. You cannot perform ion exchange chromatography when the PIs are so close to each other. Even if you use a buffer of pH 8.8, your protein B would be precipitating. So you cannot use, or your PI, all the proteins would be precipitating because your PIs are very close to each other. You cannot do ion exchange chromatography. The only thing that you can do over here is the gel filtration chromatography, because the molecular weights are different and they would be eluting at different regions. So gel filtration chromatography is the ideal thing that you can do. Okay. The next one, carboxymethyl matrix and diethyl amino ethyl matrix are generally considered as. So these are the two different matrices. So what are they considered as? Cation exchange, cation anion exchange, anion resins, and the cation, anion and cation respectively. So what is carboxymethyl matrix and what is amino ethyl matrix? This is an easy question. I guess you can give it a right answer. From the name you can understand. One is carboxymethyl and the other one is amino ethyl. So carboxy means it is negatively charged, so it will help in the cation exchange. And amino ethyl, amino, positively charged, it will help in the anion exchange. So option B is correct. Okay. Which of the following is not true about high pressure liquid chromatography? So which of the following is not true about HPLC or high pressure liquid chromatography? It requires high pressure for the separation of species. There is no need to vaporize the samples. It is performed in columns. It has high sensitivity. So if I go one by one, it's high pressure it requires high pressure for the separation of different species. It is performed in columns and it has high sensitivity. And there is also the need to vaporize the samples. So therefore option B is the one that is not true about HPLC. Moving on to the next question. Before loading the impure protein solution in the Ni-NTA chromatography of phosphate buffer pH 7.4, what will you do? So what are you going to do before loading the impure protein sample in a Ni-NTA column? Centrifuge the solution in 11,000 rpm and discard the supernet. Centrifuge the solution in 11,000 rpm and discard the precipitate. Check the pH using pH meter and equilibrate the column with mobile phase. So what will you do? A. So after centrifuging, what you will do, it will pellet down the impurities, so you can discard the impurities, right? And so you would be loading the supernet and the protein will be in the supernet, so we will equilibrate the column with the mobile phase. Say that has been said is the phosphate buffer. Okay. So checking the pH is not that important because we know the pH is 7.4. So the correct answer is D. So centrifuging and before loading, what you will do? No, no. This is not correct. Sorry. So first you will centrifuge the solution and discard the precipitate. So you have to discard the precipitate first. So 2 is correct and 2 and 4. So 2 and 4. So okay, B is correct, right? You will say centrifuge the solution and discard the precipitate because your protein is there in the supernet. If it is in there in the soluble fraction, then you can check the pH and equilibrate with the mobile phase. So B is the correct option, right? Okay, the next one. Which of the following statement is or are true? In membrane-based filtration method, commonly used to remove higher molecular weight compounds, for a common anion exchange chromatography, sodium acetate buffer is used of pH 4.5. In an affinity chromatography, only one of the proteins binds to the column material on basis of specificity and high affinity. And in gel filtration chromatography, it can separate proteins based on size. So which is true, or which of the following is or are true? So in membrane based filtration method is commonly used to remove the lower molecular weight compounds, and the sodium acetate buffer of pH 4.0 is used for a cation exchange chromatography. Okay. So these two are incorrect options. The correct options are three. That is, in an affinity chromatography, one of the proteins binds to the column material based on specificity and high affinity. And in gel filtration chromatography, it can separate based on size. So A is not correct. How can? But 4 is also is correct. I was teaching. It can separate based on size. So 3 and 4 are correct. The next one. This is a match the following. So affinity chromatography, gel filtration chromatography, cation exchange chromatography, hydrophobic interaction chromatography. And on the column material, you have silica gel, CM cellulose matrix, nickel-NTA matrix, biogel P300, and DEAE Cephalose matrix. So affinity chromatography, nickel-NTA matrix. So 1, 3, 1, 3. So A and C can be, or C can be correct. Next to gel filtration chromatography, biogel P300. Then cation exchange chromatography, CM cellulose matrix. And hydrophobic interaction chromatography, silica gel. So option C is correct. So these are the type of questions that will be there in exams, and also these are the questions that commonly you can see even in the competitive exams that you give, like the GATE, NET, and what other exams you give. So these are very interesting questions that you will be mostly seeing. Okay, so you need to be very prompt in all of these answers while giving these answers. Okay. Anyways, moving on to the next question. A sample contains a mixture of proteins from which protein X has to be isolated. So from a mixture of proteins, you need to isolate X. So which of the methods would you be using for accurate isolation? So you see that the molecular weight is 15, 26, 24, and 20. This is also around 24 kd, and the pi is 3, 8.7, 7.4, and 4.3. So which of the methods would you be using to separate X from the other compounds? This is a very interesting question. So if you see very well, that the options that are given is affinity chromatography followed by ion exchange chromatography, gel extraction chromatography, ion exchange chromatography, and ion exchange followed by gel extraction. So only if you do ion exchange chromatography, you cannot separate the proteins. So even if you are using a pH say of 6, then A and X would be on one side, B and C would be on one side, and then you do not know what to do. Affinity chromatography cannot be performed because we do not know if your protein is tagged or not tagged. or proteins can contain similar kind of tags, so it's difficult. Only if you do gel extraction chromatography, your B, C and X would be eluting at the same place, or might be you get a shoulder, you cannot separate them. So what you do, first separate them according to ion exchange chromatography. So you get A and X on one side and you get B and C. So you have separated A and X from B and C. Now you need to separate A and X. So those have the two different molecular weights. One is 15 and the other is 24. That would be eluting at different points in size exclusion chromatography. So first you perform gel extraction, ion exchange chromatography, and then you go for gel extraction chromatography. Okay. Now, next one. Your protein of interest contains 6x histidine tag and is overexpressed in bacterial culture. After purifying by nickel-NTA chromatography, you run the eluted fractions through running SDS page to confirm its presence and purity. However, you observed in addition of your protein of interest an additional band uh, is you see an additional band. Which of the following is a possible explanation for that? So what is the question telling? So you have a protein of interest that is tagged with 6s histidine. So you have 6 histidine tags, and that overexpresses very well in your bacteria. Now when you have performed nickel-NTA chromatography, you see you have got a very nice peak, and then you run it in the SDS page. Okay, in the presence of SDS, you run your protein to see whether your protein is there or not. And when you observe that particular gel image, you see that an additional band has suddenly arose. So what is the explanation for that particular situation? The his tag got cleaved, the protein does not contain a tag. In addition to your protein, some bacterial proteins can contain tandem repeats of histidine residue, or the protein is multimeric. So to answer this type of questions, there can be numerous ways you can interpret such a band. The first thing is that your histag can get cleaved. Okay, but even if your histag gets cleaved, it is just 6 amino acids. That counts for about 660 daltons. That is 0.66 kilodaltons. That is sometimes not observed in a gel image. You cannot tell that that particular thing has cleaved. Your protein does not contain a tag. That is not correct. Your protein is multimeric. That is also incorrect because you're running a reducing SDS page. So that is also incorrect. So what is correct is that in addition to your protein, some bacterial proteins can contain some repeats of histidine residues. That has also eluted along with your protein of interest. That's why you can see an additional band. Okay. And the last question for the day. Which of the following statement is true for fast protein liquid chromatography, or FPLC? The flow rate is maintained at 2 to 5 ml per minute. Increasing the flow rate beyond the limit can cause column breakage. A large air pockets can enhance the protein purity. At 280 nanometer, we can monitor UV absorbance, pH, and conductivity of the protein. And after elution, SDS page must be performed to check the purity. So, which of the following options do you feel is correct? So the flow rate is maintained at 2 to 5 ml per minute. Now if you increase the flow rate, it will damage the column because it cannot withstand such high pressure. There is a constant pressure that the pipelines or the machine needs to maintain. So one is correct. The next one is saying at 280 nanometer you can monitor UV absorbance, pH and conductivity of the protein. That is also correct. After dilution, SDS page must be performed to check the purity. That is also a correct option. What is not correct is that a large air pockets can enhance the protein purity. That is wrong. A large air pockets usually damage the machine. So 1, 3 and 4 are the correct options. Okay. So that's all from the practice problems. And that's all I had to discuss with you all. Now, if you have any questions, you can ask me, else we can end the discussion. And if you have any questions anytime, you can definitely mail me in my mail ID. Okay, so I'm just putting my mail ID. If you have questions anytime, you can just ask me. And in any ways, these video lectures are being recorded and would be be uploaded in YouTube. So you can also check back if you have any problem. You can write me there as well, or you can mail me anything that you're comfortable in. So I guess there are no questions. So thank you all. We can end the session over here.